So graph is a representation of pairwise relationship between a set of objects. So what is mean set of objects we'll see later. And terms or vertices, that is also called as nodes. Interconnection connected object are represented by points termed as vertices. Let's take a look on linked list. There is an element, data item, and the next node. The element is called vertices, and edges means arc. It determines the relationship between the pair of nodes. It gives whether it's connected, directly connected, or not directly connected. Like this, it shows the relationship between the nodes. That's vertices. Okay. Then adjacency. Two nodes are adjacent if they are connected. So there's a connection between two nodes. Then it is called adjacent nodes. But it must be connected directly. Indirect connections are directly. A connected to B and B connected. So there is no connection between A and B, A and C. These are not. They are connected, but they are not adjacent nodes. Only A and B are adjacent nodes. Okay. Then so path shows the sequence of edges. It shows the sequence of how the graph shows. The graph path goes. There's two categories: directed and undirected. That is unordered. The vertices are ordered form, that is u, v and v, u are not same. They are different in its direction. V to u is one direction and v to v is u is other direction. Okay. So unordered, that is undirected. The graph is not in an ordered form, that is u, v and v, u are the same. There is no direction, so it looks the same. So this is an undirected example for undirected graph. A, B, C, D, and A and B are adjacent edges, and A and C are adjacent, and C and D are adjacent, D and B are adjacent, and D and E are adjacent. So C and E are not adjacent nodes. Okay, because if there is an intermediate D node, so C and D are adjacent. This AB, BC, CD, BD, and D, and D, ED. So these are all adjacent nodes. Here, vertices are A, B, C, D, and E are vertices, and edges means this is one edge, this is one edge, this is one edge, this is one edge, and this is one edge. That is AB, AC, BD, CD, and DE. These are vertices. Edges or edges, arc. So it shows a relationship. A, that means A is related to B. A and B are connected. A and C are connected. C and D are connected. B and D are connected. E and D are connected. This is a relationship that's mentioned in this. If there's a graph, and if there is a next, I'll find that. So this is an example for a directed graph. A is related to 2, and there is no direction between 2 and 1. 1 is related to 3, and 3 is related to 4, and 5 is related to 2 and 4. There's no relation between 2 and 5. Okay, so implement a graph. How we are going to implement a graph is the main topic. So implement has 3 ways: adjacency list, adjacency matrix, pointers or memory for each node. Actually, a form of adjacency list. Okay, no problem. So first of all, what is the adjacency list? For example, I'll say the example 1, 2, 3, 4, and 5 are in an ordered matrix. Directed graph. That's the graph. Okay. First, 1 is related to 2 and 1 is related to 3. So 1 has a relation with 2 and 3. All of this, there is no relationship. This is a adjacent list. And 2 has no relationship. There is no direction for any of this. No, nothing. So 3 has only one relation, that is 4. We are saying 2 has a relation with 4, and 4 has a relationship with 1, and there is no other relationship, and 5 has a relationship 2 and 4, but because there is an arrow, there is an arrow represents the ordered graph. Okay. Next, undirected adjacent selects, that is 1, 2, 3, 4, 5, and here I say 1 has a relationship 2 and 3 and 4, 2, 3 and 4, and 2 has a relationship 1 and 5. 2 has a relationship 1 and 5, and 3 has a relationship to 4 and 1. 3 has a relationship 4 and 1, and 4 has a relationship 1 and 3. 4 has a relationship 1 and 3. 5 has a relationship 2 and 4. This is what is called adjacent list. The sum of the lengths of adjacent list is 2 of A in a direct graph and E for direct graph. then memory record is in the order of maximum of e comma e equal to order of e plus e. So next, adjacency matrix for an ordered list. It's an ordered graph. That is, one is relationship. One has a relationship with 2 and 3. There is no other direction. It has a relation 4, but it's not directed towards itself. Okay, so 1 has a relationship 3, 2 and 3. All others 0, 0, 0. 2 has no outward direction, so it has no relationship 0, 0, 0, 0. It has no relation to 1, no relation to 2, no relation to 3, no relation to 4, no relation to 5. 3 has relation to 4 only. 3 has relation to 4, 3, 0. It has no relation to 1, it has no relation to 2, it has no relation to 5, it has only relation to it is 4. That is 4 as 1. So 5 has a relationship with 2 and 4. 5 has a relationship 2 and 4, all others 0. Here 1 represents the relationship, its direction. It has a relationship with edges, vertices. Okay. And 0 represents there is no relationship. This is what's adjacency matrix for ordered graph. So undirected adjacency matrix. So 1 has relationship 2, 3 and 4. Here you see 1 has relation 1 has no looping with itself, there is 0. 1 has relation 2, 2. 1 has relation 2, 3 and 3. 1 has relation to 4, then is 4. 1 has no relation to 5, 0. 2 has relation to 5 and 1. 2 has relation to 1 and 5, all others are 0. 3 has relation to 1 and 4. 3 has relation to 1, there is no relation to 2, and it has a relation with 3 and 0, and it has no relation to 5, 0. 4 has a relation with 5, 1 and 3. 4 has a relation to 1, 4 has no relation with 0, so 2, and 4 has no relation with 4, 0, and 4 has a relation with 5. So 5 has a relation with 2 and 3, 2 and 4, so 5 has a relation with 1 and 2, all others are 0. Okay. So depth first search. Depth first search algorithm transfers a graph in a depthward motion and uses stack to remember to get the next vertex to start a search. So okay, first depth first. S travels A, B and D, and next go upwards and then this way, this way. Okay, first S goes to A to B, D to E. That is depthward from bottom to bottom. So sorry, top down approach. Sorry, top down approach is yes to A to B, D to G, G to E, E to B, and G to F, F to C. There's 7 transactions. Okay, so for example, from A to C to D, then first E, then F. Okay. First, visit the adjacent unvisited matrix. Mark it as visited, display it, push it in a stack. If no adjacent vertex is found, pop up a vertex from the stack. If there is no adjacent vertex found, pop up a vertex from the stack. Repeat the rule 1 and 2 until the stack is empty. Okay. Here is an example for a non-directed graph for depth first search algorithm. So 1, initialize the stack. There is no places. First, just start. Mark as is the beginning. So S is visited, so it's inserted in the stack S. And next we can go by means of C, D, B, anywhere itself. There's the address matrix A, B, and C. So first we go by means of an alphabetical order. So check it out, take A as a visitor. So just insert A, and from A here is D. There is no unvisited, there is 2 connections, D and S. So D is not visited, so we have to insert a D into the stack. So next, from the D we are going to visit B. Then C and D are unvisited, so we check it out as a B. We have to insert B into the stack, and then next S is visited, so from D we are going to visit C. So C is not visited, so we have just pop it out B, because there is no unvisited edges for vertices for D. So just pop it out, and we are inserting C into the matrix. So this is what is called what happens in the depth first search. So in the final result, S, A, D, and C are inside the stack. So D is popped out because everything is dead when compared to B.